In this video, I'd like to talk to you about the center of mass, which is a position that is defined relative to an object or a system of objects. Let's consider these bocce balls. The center of mass for an individual bocce ball intuitively lies in its centroid, or its geometric center, whereas the center of mass for this horseshoe lies in space. In other words, it is not directly on the object. Mathematically, we can calculate the position for the center of mass in a system by looking at the product of the sum of masses for the objects in the system and the position for the center of mass of the system, and setting that equal to the products of the individual objects' masses and their relative positions. Now, I will expound on what is meant by relative positions when we work through an example here in a moment. So again, in this definition, the capital M is the mass of the system, and I'm denoting the position of the center of mass with a subscript of Cm. So the ellipses in this equation are used to simply indicate if there were more than two objects in your system, you would include that third object's mass multiplied by that third object's relative position. Oh, hey, Stickman. Hey, Stickman's son. Let's use Stickman and his son to work through an example problem here. So, we're going to find the center of mass for the two-object system. And we are only doing this in the x or pure horizontal direction because the individual objects here, their relative center of masses actually lie up toward their gut torsal area. However, we're only going to calculate the position horizontally here. So each of these increments, it represents 1 meter, and I am going to choose my starting position for these two objects in the equation. I am going to choose to start on the far left side here at Stickman. And so all of my measurements, my positions are going to be relative to this chosen position. And it's one of those deals where you can work more efficiently if you choose your starting position wisely. Let me show you what I mean. So when we do this calculation here, I have the mass of Stickman multiplied by the position. Well, I've chosen my position to be right here, so the distance to there is 0 meters, which means this whole part of the expression will turn to 0. So when we're actually going through dividing both sides of the equation by the mass of the system to isolate the position of the center of mass for the system, so that's where in the denominator 75 plus 50 kilograms comes from. That's the mass of the system. Then we can go ahead and find our mass to be located at 1 meter. That is 1 meter from our chosen reference point, which was Stickman. So the center of mass for this system is right here. 1 meter to the right of the chosen reference point, which again was starting at Stickman. So the center of mass is going to follow Newton's second laws. Now remember what that means here, that if we have a net external force, that can lead to an acceleration in the direction of that net external force. Well, when we're considering a system here, the force must be external to the two-object system. In other words, any forces within this system will not lead to an acceleration. Let me show you what I mean here. So Stickman and Stickman's son are on an ice surface. So mu equals 0. And they're going to use this rope to pull on each other. So kind of like a tug of war type deal. And Stickman is going to basically move his stick son toward him. Again, we are on a frictionless surface, so the coefficient of friction is equal to 0. And the statement is that the center of mass for this two-object system will remain at rest unless there is some net external force. And I've said that. Well, in this case here, we have Stickman and Stickson, and look where they meet. They meet at their center of mass. Now, we'll do this in class as well. You can do it with meter sticks and other things, and I'll show you how this works. But if they both pull on each other, they will ultimately meet at their center of mass. There were no external forces to the two-object system. So what did the center of mass do? It remained at rest. It is still exactly where we calculated it in this example. So now I want you to consider the center of mass with reference to the light blue colored ball and the magenta ball that I've been using throughout this unit. Let's go ahead and calculate the center of mass for this two-object system. And of course, you can find each object's individual mass because you are given its momentum. And you know that its momentum is the product of mass and velocity in this unit. So we can actually calculate the speed of the center of mass for a system as well by using this same equation, except instead of position, we have the relative velocities. We can calculate the velocity of the center of mass. But first, I want you to pause the video and try to calculate the center of mass position for this two-object system. When doing so, we have the mass of the individual objects, and please note that my chosen reference point was on the light blue colored ball. So everything is with reference or relative to my chosen position. It's completely arbitrary, guys. I could have chosen to start way over here, and that is my reference point. You will get the exact same answer. This is just a more efficient approach. So I find the center of mass for this two-object system to be 0.5 meters to the right of my chosen reference point, which was the light blue colored ball. So now we can go ahead and calculate the center of mass and its speed. Let's go ahead and look at this PHET simulation here, in which these two objects are colliding. We're going to show that the center of mass speed is 0.63 meters per second. We're going to use this equation here, which we've substituted now in their relative velocities. Of course, the mass of the system is found to be 2 kilograms. And then VCM is representative of the velocity of the center of mass for this two-object system. I have each object's speed, and I have paid attention to signage, which brings me to the point when you're calculating whether it's the position of the center of mass or the velocity of the center of mass. Signage is of the utmost importance, so please be aware of that. When we solve for the velocity of the center of mass, we find it to be 0.63 meters per second, and that's in the positive or rightward direction, as you can see on this simulation. The center of mass remains at rest. Yes, we can say that. But why? And as some of you may have surmised, the answer lies in Newton's third law. So going back to our two object system, those two objects form a mutual pair in which the force of one object onto the other is equal in magnitude but opposite in direction. I want to talk to you about the motion of the center of mass of a two object system and rotation. So we will be talking about rotation in upcoming units. This animation here shows that when this object is struck at its center of mass, it goes upward in the straight linear direction vertically. However, when this object is struck any other position, the object rotates about its center of mass. So anytime we have a system or an object that is struck at its center of mass, the location that you now know how to calculate, that object will move off in a straight line, whether that's a straight left to right or, as this animation shows, a vertical line. It will not rotate. It will follow translational or linear motion. Now let's look at the motion for a three-object system. Following the center of mass for this animation here, you will note that it follows a perfect parabola. So just like we discussed in our studies of kinematics and two-dimensional projectile motion, this system of objects and their center of mass follows Newton's second law in this beautiful parabolic trajectory. No difference whatsoever. So this center of mass obeys Newton's second law, as you can see in this animation. In this video now, I've taught you about the center of mass for a two-object system. We've looked at it both quantitatively and qualitatively, and now you should be able to analyze data to find momentum and to relate that to the center of mass, not only now of an object, but for a system of objects. And I'll see you guys in class.